Okay, so in last class we were discussing batch normalization. So mainly we were discussing the regularization methods which are used to overcome overfitting problem in neural network, right? So I think we discussed what's the need for batch normalization. But if not, like if you want revision, then let me quickly revise it. That why is it required? Okay. Yeah, can you see the slides? Like I have shared two windows. I don't know which is, you can see slides, right? I have shared one Word document as well as PPT. So what can you see now?
Ma'am, PPT is visible. Batch normalization need.
Okay, fine, fine, fine. Okay. Okay, so as we discussed, like this is one of the regularization technique, no, batch normalization. Its need was also discussed with respect to this diagram. And if you remember, we discussed in this diagram that initially our inputs x1 to x4, which are shown in this figure, right, they are in normalized form as they are coming from the pre-processing stage of the data science pipeline, right? And this modeling, data modeling is almost the fourth step in data science pipeline. So when this data is fed to the input layer of neural network, they are in normalized form only. But when input passes through the first layer, it transforms that input. So how it transforms? So if you remember, we discussed that when input is given to the input layer, that input is multiplied to weight values, and this dot product of input and weight value, it is given to activation function, and let's say sigmoid function. So when this dot product of input and weight value is passed to sigmoid function, it gets transformed. So not only at this layer, but we know that there are multiple hidden layers. As you can see in this diagram, multiple hidden layers are there. And at every layer, this happens that, okay, now when you get output from the first hidden layer, it is multiplied with weight value. Okay, output from the first hidden layer. Okay, it is multiplied with input weight value. And again, it is given to the activation function. So again, your value is transformed. So output of each hidden layer, which is multiplied by weight value and then given to some activation function, it is transformed. So this transformation take places for every layer, every hidden layer in the neural network, second layer and so on. And it goes till the last layer. Like this transformation happens till last layer. So though we are presenting normalized input to our neural network, it does not remain in the same form when it passes through all layers and when it comes at the end, last layer of the neural network. Okay, and that's why like we need batch normalization. So here you can see that like how it is transformed in figure below. You can see that red color box shows that input values are in normalized form. But you can see that below here, I have mentioned that how it is transformed. So here, X is the input from the input layer. It is multiplied with weight vectors here, W1. And then this sigma is your activation function. And then this is the output. H1 is the output from first hidden layer. Now this output to the first hidden layer, you please look at this second formula. That output is multiplied with this like output from this hidden layer. This is your input layer. Okay, input layer. This values x1 to x4, which are presented to this input layer, they are multiplied with w1 and then passed to activation function. Okay, so that becomes the output of the first hidden layer. Okay, now output of the first hidden layer here, this is your first hidden layer. Okay, so output of this first hidden layer, it is multiplied by weight vector W. Then again, it is given to some activation function in second hidden layer, and then you get the output at the second hidden layer. So here you can see that W2 into H1. And what is H1? H1 is this. So this happens till your input, like this happens through all the hidden layers till the last hidden layer in your neural network. And when activation function is applied to that dot product, that value is transformed and it does not remain in normal form. So that's why like it is required to apply the batch normalization. Okay, so although our input was normalized with time the output will no longer be on the same scale. As data go through multiple layers of the neural network, L activation functions are applied because L hidden layers are there. So number of activation function is equal to number of hidden layers in your neural network. So if there are L hidden layers, L activation functions are applied when data is passed from input to output layer, and it leads to an internal covariate shift. This is very popular term, internal covariate shift in the data. So how batch normalization work? I'll let you know how batch normalization work to overcome this problem, which is known as internal covariate shift in data. So let us see now how batch normalization works. So there are two steps for batch normalization mainly. The first step, as you can see that input is normalized, and in second step, rescaling and offsetting is performed. So our first step is input is normalized. What is normalized? Normalization, it is the process of transforming the data to have mean value as 0 and standard deviation as 1. So normalization of data means make mean 0 and standard deviation 1. So how we can achieve that, I'll show you. So in this first step, first mean is calculated. Okay, I'll show you all these terms. So first mean is calculated here using this formula. You can see that the formula of mean is given. Okay, in this step we have our batch input from hidden layer H, and first we need to calculate the mean of this hidden activation. It is here M is the number of neurons in hidden layer. Okay, so HI means sigma HI. I represents the number of hidden layer. M represents the number of neurons, and mu represents the mean value. So mean value is calculated like this. Once we have calculated the mean value, the next step is calculate the standard deviation of hidden activations. So standard deviation is calculated like you can see that the formula is square root of 1 upon m sigma hi minus mean value. Mu is mean value. So we are calculating it using this formula, standard deviation. So mean value and standard deviation are calculated. Further, what we will do, as we have the mean and the standard deviation ready now, we will normalize the hidden activations using these values. I hope you understand this point, what we are discussing now. We discussed that the data does not remain in normalized form when it passes through the different hidden layers of the neural network. So how to keep it in normalized form? How to normalize it when it is not in normalized form when it comes out from the hidden layer? So to keep it in normalized form, what we do here, we perform two steps when we get output from the hidden layer. So two steps are performed on output of the hidden layer, every hidden layer. Okay. So which two steps are performed? So first mean value is calculated considering the nodes in that hidden layer. Then standard deviation is calculated. And then we normalize like that output of the hidden. Why we call normalize input? Because it becomes the input to the next hidden layer. The output of one hidden layer, it becomes input to the next hidden layer. So we need to normalize it before we present it to the next hidden layer. So every layer in the neural network should get data in normalized form. First layer is automatically getting because it is getting data from pre-processed step. So the first input layer is getting data in normalized form. But when we get output from the first hidden layer, it does not remain in a normalized form, and so we need to normalize it. So the first step is compute the mean, then compute the standard deviation. After computing the standard deviation, what we do here, as you can see further, we normalize now hidden activations using this mean and standard deviation. For this, what we do, we subtract as given in the third formula. We subtract the mean from each input and divide the whole value with the sum of standard deviation and smoothing term epsilon. You can see that smoothing term epsilon is added to standard deviation. So we do this for for each input, and this smoothing term epsilon assures that it assures numerical stability within the operation by stopping a division by a zero value. So this is how you can see that the H norm on the left hand side, you can see that it is H norm because we are performing normalization on output from the hidden layer so that we can present normalized data to next hidden layer. So this is the first step. Okay, now after this, what is the next step? Later, rescaling, as I told you, two steps, rescaling and offsetting is also resetting and offsetting is also performed. So what is this rescaling and offsetting? If the final operation, the rescaling and offsetting of the input take place, then finally we get the data to be presented to next layer. Here, these two components of batch normalization come into the picture, and they are gamma and beta, as you can see in this formula, gamma and beta. Gamma represents rescaling and beta represents shifting. Gamma represents rescaling and beta represents shifting, that is offsetting of the vector containing values from the previous operations. So these two are, this gamma and beta parameters, they are learnable parameters during the training of neural network, and they assures the optimal values of gamma and beta. Okay, and that will enable the accurate normalization of each batch. So this is how this two this is how batch normalization is performed. Only two steps, I repeat, where these two steps are applied. These two steps are applied on the output of the hidden layer so that the output of a hidden layer can be normalized, the data can be normalized and can be presented to next hidden layer. Normalized data can be presented to next hidden layer. So these two steps are applied to output of every hidden layer, okay, to normalize the data. Okay, so this is how batch normalization is performed. Now, what are the advantages of batch normalization? As you can see, like major four advantages are there. Let's discuss these advantages one by one. The first advantage is it speeds up the training of neural network. It speeds up training of neural network. By normalizing the hidden layer activation, batch normalization speeds up the training process. So how, when we say that it speeds up the training of the neural network, actually because it handles two things. First thing, it handles internal covariate shift of data. I told you some time that this is very known term in neural network terminology, internal covariate shift. So what is internal covariate shift? I'll explain you this with example. We ensure that using this internal covariate shift, like it is a problem, and we ensure that the input for every layer is distributed around the same mean and standard deviation. If you are unaware of what is an internal covariate shift, let us discuss it first. Okay, so suppose, okay, let me explain it with example. Okay, suppose we are training an image classification. We are training a model for image classification. We are training one model, means one neural network for image classification. And that neural network is expected to classify the image into dog or not dog, whether the presented image contains dog or it does not contain the dog. That decision it has to give. Now, let us say we have the images of white dogs only in our data set. Let us assume that in our data set, images of dogs are only white. And these images will have certain distribution as well, right? So using these images, model will get trained, neural network will get trained, and it will update its parameters. Okay. Now, later, after once we have trained our neural network model with this data, now you can see that this is only white colored dogs. Okay. Now, after we train our neural network model with this white colored dog, what happens if we get a new set of images consisting of non-white dogs? Then the output will be correct or not. This new images will have a slightly different distribution from the images of white dogs. It is but obvious, right? Images of white dogs, they have certain distribution, and the images of some other color dog, they have slightly different distribution. Now the model will change its parameters accordingly to this new images, right? So the distribution of the hidden activation will also change. And this change in hidden activation, because there is a change in distribution because of like a new data, distribution of hidden activation will also change. And this change in hidden activation is known as an internal covariate shift. It is known as internal covariate shift. Okay, and this can be overcome using batch normalization. This problem can be overcome using batch normalization. Second thing, as we can solve this problem using batch normalization, like it helps us ultimately to increase the speed. Second thing, how it helps us to increase the speed is it smoothens the loss function. Batch normalization smoothens the loss function that in turn, by optimizing the model parameters, improves the training speed of the model. So batch normalization is of huge research interest, and a large number of researchers are working around on this batch normalization. So if you are looking for further details on this, then you can go through like batch normalization, how to accelerate deep network training by reducing internal covariate shift. How does batch normalization help optimization? You can search on all these topics in Google, and you will get a lot of information. Okay, so the first advantage is it increases the speed of neural network training. Second is it improves generalization. The second advantage is it improves generalization. By normalizing the activations of a layer, by normalizing the activations of hidden layer, batch normalization can help us to reduce overfitting and improve the generalization ability of the model. Third is reduce need for careful initialization. So batch normalization can help us reduce, it helps in reducing the sensitivity of model to the initial weights, making it easier to train the model. So that way, like it reduces the need for careful initialization of weight values. And the next advantage is it allows for higher learning rates. Batch normalization can allow the use of higher learning rates that can speed up the training process. If learning rate is slow, the training will be slow. If learning rate is fast, like it is high, then speed of training would also be high. So batch normalization allow us to use higher learning rates, right? And that way also it helps us to speed the training of neural network. So uh, these are the advantages of batch normalization, that it improves generalization, reduces the need for careful initialization, and it allows for higher learning rates. Okay. Now this is the next, way to overcome the overfitting problem. Like there are multiple ways to overcome the overfitting problem, and batch normalization is one of them. Okay. But if you remember, I told you in last class that there are multiple ways to overcome overfitting, like batch normalization, early stopping, dropout, and pruning. So dropout we discussed in last class, in last unit. So we will not repeat it because the same theory, like we should, no need to repeat the same theory. Let us discuss now early stopping and then pruning. That how early stopping and pruning also help us to overcome overfitting problem. Okay, so as we know, regularization is kind of a regression where the learning algorithms are modified to reduce overfitting, And this may incur a higher bias but will lead to lower variance when compared to non-regularized models. Okay. Okay. Now, before we discuss this early stopping, let me discuss one point, that how our given data set is divided into different sets, like training set, validation set, and testing set. In general learning algorithm, in general learning algorithm, data set is divided into training set and test set, two divisions. Okay. And it may be like the ratio may be 80 percentage training set and 20 percentage of data may be used as testing set. Or it may be 90 is to 10, or it may be 70 is to 30, like 70 percentage data may be used as training data and rest 30% data may be used as testing data. Okay. So data set is usually divided into two parts, training set and testing set. After each epoch of the algorithm, after each epoch of the training, the parameters are updated accordingly after understanding the data set. Finally, this trained model is applied to the test data. Finally, this trained model is used for test data. Generally, the training set error will be less. Okay, now be with me, please. Please understand this. The training set error, the error for training data will be less compared to error for testing data. This is because of overfitting, whereby the algorithm memorizes the training data and produces the right results on the training data. So the model becomes highly exclusive to the training set and fails to produce accurate results for other data like test data. Okay, so regularization techniques are used here to reduce overfitting and to increase the performance of the model on any general data set. And early stopping is a popular regularization technique due to its simplicity and effectiveness to overcome this problem. Okay. Okay. So what is early stopping? As mentioned here, it is an optimization technique used to reduce overfitting without compromising on model accuracy. It is used to reduce overfitting without compromising on model accuracy. And the main idea behind early stopping is to stop training before a model starts to overfit. Stop training, early stop. When stop training before model starts to overfit. Okay. So how this can be achieved with early stopping mechanism, let me explain you. Regularization by early stopping can be done either by, okay, there are two ways how we can achieve this. These are the two ways how we can achieve it. Regularization by early stopping. Okay. So there are two ways. The first way is divide the data set into training and test set and then use cross validation on the training set. Divide your given data set only in two parts, training and testing, and then use cross validation technique on the training data, training set. That is the first way. Second way is divide data set into training, validation, and test sets. Three sets. Now data set is divided into three sets. Training, first it is divided into two sets, training and testing, and then the part of training data is considered as validation set also. So ultimately, like there are three partitions, training set, validation set, and test set. In which case, cross validation is not required because now we are using validation set also. Now, in this second case, we will use second case to discuss this early stopping mechanism. In the second case, in early stopping, algorithm is trained using the train set. And the point at which to stop the training is determined from the validation set. For training set is used, and the point at which to stop, the point at which the training should be stopped is determined from the validation set, as you can see in this diagram. Training error and validation error are analyzed. The training error steadily decreases while the validation error decreases until a point after which it increases. You can see in this diagram. Training error steadily decreases. You see this curve. And validation error decreases until a point. It is a U-shaped curve for a validation error. So a validation error decreases until a point, and after that point, it increases. So this is because during training, the learning model starts to overfit the training data. And this causes the training error to decrease while the validation error increases. So model with better validation set error can be obtained if the parameters that give the list validation set error are used. And each time the error on the validation set decreases, a copy of the model parameters is stored. And when training algorithm terminates, this parameter which gives the list validation set error are finally returned and not the last modified parameters. Okay. So in regularization by early stopping, we stop training the model when the performance of the model on the validation set is getting worse. That is increasing the loss or decreasing accuracy or poor values of the scoring metric. So you can see that by plotting the error on the training data set and the validation data set together, both the errors decrease with a number of iterations until the point where the model starts to overfit. And after this point, the training error still decreases, but the validation error increases. So even if the training is continued after this point, early stopping essentially returns the set of parameters that were used at this point, and so is equivalent to stopping training at this point. This is very important. So the final parameters return will enable the model to have low variance and better generalization. So this is how this early stop mechanism works. Okay, and next is pruning. Now this is a very huge topic, pruning. Since years, researchers are working on this pruning, that how pruning can be used to accelerate the performance of neural network. Okay. And for your information, like here I have included this, I'll show you. Uh, okay, I'm not able to switch it. Just a second, I have kept it open, but can you see this PDF file? Or you can see
Yes,
only
ma'am.
slides?
Yes, ma'am. PDF is visible.
Yeah. So students, like it's a huge topic. This paper is under review. Like this is done by this work is done by my PhD scholars. And here you can see that the pruning methods for acceleration of convolutional neural network. Okay, so this is a very huge topic, and just I wanted to show you, and that's why like I have kept this paper open, because in this syllabus, like after this topic, we will start discussion on this convolutional neural network. And this paper is mainly to accelerate the performance of convolutional neural network only. So I would like to show you that though I'll discuss very briefly in your syllabus that how pruning is useful to increase the speed of neural network and how it helps to generalize the model. But I would like to show you that it's not that much like a very, it's not a small topic. Okay. I would like to show you here that there are several techniques to increase the performance of convolutional neural network. How we can accelerate the training of convolutional neural network. So they are mainly divided in two categories: hardware-based acceleration methods and model compression methods. So hardware-based means you have to use uh, more computing power, like additional computing power, and you have to use powerful machines to increase the speed of CNN, to increase the training of convolutional neural network. That is hardware-based acceleration method. But usually researchers and in practice, uh, people prefer this model compression methods, that how you can compress this CNN model, because its architecture is sometimes complex if you use more number of hidden layers in this CNN architecture. If it is shallow CNN, then there would be less number of parameters. But if it is more number of hidden layers are used in architecture of CNN, then its architecture becomes complex and we need to compress it. So these are the different methods to compress this CNN: quantization, knowledge distillation, low rank decomposition, and network pruning. And you can see that under this network pruning, there are again three types of pruning: filter pruning, channel pruning, and connection pruning. So in your syllabus, like one topic is included pruning. So pruning is one of the model compression method, and there are different kinds of pruning methods: filter pruning, channel pruning, and connection pruning. Again, this though we have three kinds of pruning methods, I'll show you that this filter pruning is further classified in uh, different methods, filter pruning. Okay, because this paper focuses on filter pruning. So I'll show you uh, just a second. A diagram is there which shows all the filter pruning methods. Okay, now here you can see that this is a section on filter pruning. So pruning includes three types of pruning: filter pruning, channel pruning, and connection pruning. As this paper focuses only on filter pruning, here you will see that even in filter pruning, there are several methods. Oh, the diagram, I'm missing the diagram. Just a second. Okay. Okay, where is the diagram? The diagram is missing here, but I was talking about this diagram. You can see this diagram. Can you see this diagram in slide? That there are four types of filter pruning methods. And they are categorized based on this, based on purpose of pruning, based on network element removing strategy, based on regularization norm, and based on label pruning. Right? And filter pruning, see this, based on label pruning, like there are four: filter pruning, channel pruning, connection pruning, and layer pruning. So so many methods are available in literature for pruning, and still research is going on in network pruning, neural network pruning. So what exactly this network pruning is? Uh, Network pruning is model compression, neural network model compression used to reduce the computational complexity of that network by removing irrelevant elements such as filters, channels, connections, layers, right? So they are removed so that number of parameters will be reduced, and you will be surprised to know that when we apply these methods, many times, like suppose there are 1 crore parameters for a complex network I have created, then many times they become half, like 50 lakhs or lesser than that when we apply this pruning techniques. And it saves a lot of time in training this. It saves a lot of time. Okay. So that is how it helps us. So, but I'll not discuss this pruning in detail now because we will be learning CNN mainly in this syllabus. And as we will be learning CNN, I think we should learn the methods which are used to prune CNN models. So once we learn CNN, we will discuss this CNN pruning methods. Okay. So this is all about the second unit. This is all about the second unit. I think all topics have been covered. Now, if you have any question related to this, let us discuss the question and then let us start the third unit. Okay, so I am ready to take your questions now related to this unit. Yeah, no question. Okay, if there are no questions related to this, then let us start the next unit then. Okay. CNN, convolutional neural network. So these are the main topics of the third unit: basic structure of convolutional neural network, the convolutions for images, the fundamental terms related to convolutional neural network, which are padding, striding, and pulling. And finally, we'll see some use cases of CNN related to image classification. Okay. So let me first introduce the CNN. CNN is an extension of traditional multi-layer perceptron. Now try to remember what is that perceptron. Okay, so we discuss single layer perceptron and multi-layer perceptron. So CNN is extension of traditional multi-layer perceptron, and it is a special kind of multi-layer neural network. This is like a feed-forward network that can, if you remember during the discussion of first unit, we also discussed feed-forward neural network and back propagation. So CNN is a feed-forward network that can extract topological properties from an image. Okay. Then CNN are designed to recognize visual patterns directly from pixel images with minimal pre-processing. This is very important point, and this we will nicely discuss that how it helps us to process images in less time. If you do not use CNN and if you use some other models or other ways to process images, they take more time in processing those images compared to CNN. CNN recognize visual patterns directly from pixel images, and that too with minimal pre-processing time. And CNN can recognize patterns with extreme ability too, such as handwriting, handwritten characters and so. Okay. So this is like a brief idea about the CNN. The CNN was invented by Jan LeCun. I told you, if you remember, during the discussion of topics of first unit, that he has like pioneer of CNN and CNN's extension. He is chief AI scientist of Facebook presently, Jan LeCun, and he has like 2020, he also invented self-supervised learning, which is a new type of machine learning technique. So he invented this CNN, and at that time he was with, you can see that, MIT, right? Okay, so let us first discuss why do we need CNN. Please understand this thoroughly, that why should we use CNN? What is the problem with feed-forward neural network, and that allows us, that motivates us to CNN? Okay, so let us first discuss this, that why this. Okay, so here you can see that this figure shows you classical computer pipeline to detect and classify the objects in input image, to detect and classify. Many people, they misinterpret these two words. Many people say that detection and classification, they are the same thing. No, they are not the same things. Detection means you are detecting the object, and after detecting the object, like in one image there may be 5 objects, so you may like your algorithm may detect 5 objects, and once the 5 objects are detected, your algorithm may or may not be able to detect all those 5 objects, may detect 4, may detect 3, right? But your image contains 5 objects. So the first task is detect the objects in the image and then classify it in appropriate class. For example, suppose in this image, you can see that kid is also there, dog is there, ball is there, right? So maybe there are classes like animals, human, toys. So they should be classified in those appropriate classes, that this is human, this object will be in human class, this dog object will be in animal class, this ball object would be in toy class, and so on. So that is classification. So this figure, like the figure at the top, it shows you the classical computer vision pipeline to detect and classify the objects in input image. Now, as we know, feature extraction is a more is a core component of computer vision pipeline. If you want to correctly classify, if you want to correctly identify these objects, then features should be extracted like uh, 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 right features should be extracted. So in traditional machine learning problems, now I'm talking about the machine learning, okay? In traditional machine learning problems, computer vision pipeline, we spend good amount of time in manual feature selection and engineering. You can see that manual feature extraction. In this process, we rely on our domain knowledge, like the because it is manual. Okay, so we rely on our domain knowledge or partnering with domain experts to create features which make machine learning algorithms work better. And some of the handcrafted feature sets are like you can see that here okay, here I have not mentioned them, but some of the handcrafted feature sets are histogram of oriented gradients, which is known as hog, har cascades, scale invariant feature transform, which is known as shift, speed up robust feature, which is known as surf. These are very popular in this computer vision domain. Hog, shift, surf, these are local feature detector and descriptor. Okay, so they are used. And we then feed the produced features. The features are produced. And here you can see that handcrafted features. The handcrafted features are produced. And then these features are given to classifier like support vector machine or ADA boost to predict the output. So this is how objects are detected and classified using machine learning. Okay, using machine learning. Image is there, we use these methods like surf, hog, shift, because these are the handcrafted feature sets. And then we extract the features from this, like manually features are extracted and they are provided to learning algorithms like SVM, ADABOS. These are machine learning algorithms. And then this machine learning algorithms, these are used for classifying those objects into appropriate class. However, the key disadvantage of this classical computer vision pipeline to detect and classify the object is that these are the key disadvantages. Feature extraction is domain specific. Feature extraction is domain specific, and we spend a good amount of time in manual feature selection and engineering. This is the biggest advantage with this machine learning based computer vision pipeline, that we spend a good amount of time. Okay. So this disadvantage can be overcome using deep learning based computer vision pipeline. Now, instead of machine learning, what if we used deep learning based computer vision pipeline? So now look at this figure. In deep learning, if we use a deep neural network, we don't need manual feature extraction. So first thing, use of deep learning model overcomes the problem of manual feature extraction. So we don't need to manually extract features from the image, and the network automatically extract features. That deep neural network automatically extract features and learns their importance on the output by applying weights to its connections. So here feature selection using deep neural network, feature like it's not manual, it is using deep neural network, and classification is also using deep neural network. Well, if you remember here, this is manual and this is using machine learning algorithm. But here, like this feature selection and classification, both are done by deep neural network. So manual feature extraction is not required. You feed raw, like when we use this deep neural network, what we do, we feed raw image to the network. And as that raw image passes through the network layers, it identifies patterns, that network identifies patterns within the image to create features. These deep neural networks can be thought of as a feature extractors plus classifier. If you have seen here, I have written, right? It is feature extractor plus classifier. So only one deep neural network performs two tasks, feature extraction plus classification. While in machine learning based computer vision pipeline, feature extraction is done manually, and classification is done by machine learning algorithm like SVM, ADABoost. But here the deep neural network itself performs both the tasks, feature extraction plus classification. And this deep neural networks can be thought of as, that can be thought of as feature extractors plus classifiers. So it is end-to-end trainable, pipeline, which is different compared to traditional machine learning models that use handcrafted features. So in this approach, an algorithm scans the data to identify features which correlate and then combine them to promote faster learning without being told to do so explicitly. And this ability helps data scientists to save a significant amount of work. So this is how it works. Like, see this. Here, there's two steps, different things. And here also there are two steps, manual feature extraction, and this is classification. But here you can see that only that one deep neural network performs that task. Okay. So this is the motivation, like it automates feature extraction based on training data and it combines feature extraction with classification. So this is the motivation behind using deep neural networks. Okay. Okay. So now, after discussing the motivation for deep neural network, let us discuss why CNN for computer vision. Why CNN for computer vision? Okay. Uh, so why not feed forward neural network? We already have feed forward neural network, okay, and some other neural networks. Then why convolutional neural network? Why not those neural networks for computer vision or for processing of images? So let me first explain you problem with feed forward neural network. If you have a notebook and pen, it would be good to compute the terms which I'll discuss during the discussion of this slide, or you can use Kelsey in your mobile. And but be with me when I discuss numbers included in this slide. Suppose you are working with MNIST dataset. Now let me tell you first what is MNIST dataset. MNIST dataset contains black and white images of characters, handwritten characters. MNIST dataset, very standard dataset. It contains black and white images of handwritten characters. Now, suppose we want to process this MNIST dataset. What it contains? It contains images. Which kind of images? Black and white images. It contains images, black and white images, and we want to process these images in MNIST dataset. All these images in an MNIST dataset, their resolution is 28 cross 28 cross 1. Now I'll explain you here what is this 28 cross 28 cross 1. Please be with me. It is black and white dataset. Okay, so intensity values are there for black channel and intensity values are there for white channel. So 28 cross 28, like 28 cross 28, it represents the resolution of black and white. And this is one because this is not color image. If it would have been color image, then there would have been three numbers. One for red, one for blue, and one for green. But these are black and white images and they are 28 cross 28 cross 1 resolution, black and white images. So, okay. Uh, how do you feed image to neural network? I tell you how we feed image to neural network. Suppose image resolution is or image size is 28 cross 28. So what does it represents? 28 cross 28 pixels are there. 28 cross 28 pixels are there. So 28 rows and 28 columns. So those many pixels are there. So total how many pixels are there in your image? 28 cross 28 means if you multiply 28 by 28, it is 784. So 784 pixel values are there in one image of this MNIST dataset. Each image contains 784 pixel values. Okay, pixel Mobile phones have very good cameras these days, right? And usually the pictures taken by mobile phones, they are in megabytes. Let us assume that the picture taken by your mobile phone is of 1 megabyte. The size of that picture is 1 megabyte. So 1 megabyte, what does it mean? 1 megabyte means 10 raised to 6 multiplied by 10 raised to 6. Okay, or 10 raised to 6, sorry, 10 raised to 6. Okay, so 10 raised to 6 means those many 10 raised to 6 neurons are required in your input layer to fit those 10 raised to 6 pixels in your image. So this is how image. So imagine the complexity of neural network when you create it to process the images. Because today we have, and if you talk about the images taken by ISRO and NASA, they are in exabytes. That is 10 raised to 18. That is not even 10 raised to 6. It is 10 raised to 18. Right? So those images, the satellite images, their size is very high. And when those images are processed, you can imagine the complexity of neural network because we have to feed each pixel to neural network to feed that image. So if there are 10 raised to 6 pixels in your image, 10 raised to 6 neurons will be there in input layer. If there are 784 pixels in your image, 784 neurons will be there in input layer of your neural network. Okay, I hope this is clear to everyone that how we feed image to neural network. Okay, so all the MNIST images, they are of size 28 cross 28 cross 1. So total pixels are 784. So in your input layer, 784 neurons are required. Okay. Now, total number of neurons in input layer is 784, and this can be manageable because it's a small 784 is a small number compared to like today's complexity of advanced neural networks. Now, what if the image size is say 1,000 cross 1,000? 1,000 cross 1,000 means you need 10 raised to 6 neurons in your input layer because you want to process 1,000 cross 1,000 image. So this many 1,000 cross 1,000 matlab 10 raised to 6 pixels are there in your image, and to process those 10 raised to 6 pixels, 10 raised to 6 neurons are required in your input layer. Oh, this seems a huge number of neurons are required for operation, and it is computationally ineffective, right? It is computationally ineffective to have this many neurons in input layer. Okay, not only this, I'll explain you. आपके इनपुट लेयर में 10 रेज टू 6 न्यूरॉन्स है, उतनी वेट वैल्यूज चाहिए, उतने कंप्यूटेशंस होंगे, फिर हिडन लेयर्स में भी वैसे ही जाएंगे. So like this when we process images using neural networks, those neural networks involve a very high amount of computation, very high amount of computation. So here comes like convolutional neural network. In simple words, what CNN does is it extract the feature of image and convert it into lower dimension. It extract the features and convert them into lower dimension without losing its characteristics. In this example, we can see that how it reduces the image into lower dimension that I have explained you with this example. Okay. Now, in this example, you can see that initial size of image is 224 cross 224 cross 3. Why 3? Because it is color image. When it is color image, 3 channels are there. RGB, red, green, blue. So 224 cross 224 image, and there are 3 channels. Okay, intensity for each pixel, there will be 3 intensity value. Red intensity value, green intensity value, and blue intensity value. So this is the size of the image 224 cross 224 cross 3. So this many neurons are required, okay, to feed this image. Now, if you proceed without convolution, then you need 224 cross 224 cross 3 is equal to almost this many 1 lakh 300. Okay, sorry, this number 1 lakh 50,528 number of neurons in input layer. But after applying convolution, your input tensor dimension is reduced to here. You can see that this is the it gets reduced at every layer in convolutional layer. So it is from this, it is reduced to this. From this, it is reduced to 112 into 112 into 100 and 128. From that, it reduces to 56 cross 56 cross 256. Then it is reduced to this 28 cross 512. And finally, it gets reduced to 1 cross 1000. So now your original image is represented by this size of image 100, 1 cross 1 cross 1000. It means you only need now 1000 neurons in first layer of feed forward neural network instead of this 1,50,528 neurons, because the dimension of input image is reduced by convolutional neural network. So what is the main job of convolutional neural network? Its main job is it reduces the dimension of image. So this was the original dimension of image, and this dimension is reduced to this. So when you multiply 224 cross 224 with 3, the number is 1,50,528. Its dimension is reduced to 1 cross 1 cross 1000. And so now only if you multiply these three numbers, only 1000 neurons are required in your feed forward neural network. So that is the main job of convolutional neural network, that it reduces the dimension of image from high to low. No, there won't be data loss. I'll discuss this, Paras, when we will discuss the convolutional neural network, that how it maintains the information and without loss, this image dimension is reduced. So that is the main thing, because if there would be loss in information, then there won't be accurate classification. We won't be able to classify image in appropriate class, right? So this is without the loss of information. Okay, so here there is another example I have included that, okay, what's the time? 7. I can complete this example. Okay, now this is CAT. Its resolution here, you can see that this is 64 cross 64, and we can have better image of this cat. If resolution is high, we know that always the resolution is high means the picture is better, 1000 cross 1000. Okay, now we want to classify it. Okay, we want to classify the image fed to this neural network, whether it is cat or not. So we have x1 to xn input elements for input layer, and 60, if it is 64 cross 64 image, this is 4094 pixels are required in neurons are required in input layer, because this is sorry 6 sorry, I'm very sorry, it is 64 cross 64 resolution is, so 64 cross 64 is 4094 pixels, 3 chiral channels, red, green and blue. So this number will be multiplied by 3, because we will have, for each pixel, we will have 3 intensity values: red intensity value, blue intensity value, and green intensity value. So that's why we are multiplying this 4094 by 3, because for each pixel, we have 3 intensity values, and all these values should be fed to neural network. So 4096 multiplied by 3, and that is approximately 12K. So if we want to process this 64 cross 64 image, 12K neurons are required in input layer. Fine. Now, because we have like 3 color channels. See, this is how, like 3 color channels. So 64 cross 64 red channel, 64 cross 64 green channel, and 64 cross 64 blue channel. And that's why that number results in 12K. Fine. And these are the okay. And if it is 1000 cross 1000 image, better resolution, then it requires 1000 cross 1000, 1 million pixels multiplied by 3. It requires how many pixels? 3 million. So 3 million input elements will be there in your input layer of neural network. Can you imagine this network? 3 million input elements. Okay. And this is also like not a common size, 1000 cross 1000. Today, common size is megabytes. right? Kilobytes, megabytes. But even with 1000 cross 1000, we need how many input elements in input layer? 3 million. Okay. Now, so it's very like difficult. And we assume that a hidden layer has 1000 neurons. It may have greater than this. These are 3 million input neurons in input layer. So hidden layer, accordingly, the hidden layer will also have more neurons. But still, we have assumed that 1000 neurons. Now imagine that this 3 million input elements will be multiplied by 3 million weight values. So 3 million multiplication will happen only at this part. Okay, then that will be fed to hidden layer again, like activation will be applied, output will again will multiplied with weight value and so on, right? So very high amount of computation is involved. Okay, so now the point is how the CNN helps us to reduce this computation, this huge amount of computation involved in our normal fit forward neural network. So how CNN helps us to reduce this computation? Okay, so we will discuss this with example in next class. But before that, I would like to take your questions related to this introduction discussed related to the CNN introductory part. Okay, so I request your friends to attend the classes now, because now I have started CNN, and if they will miss this part, they'll not be able to understand the topics which I'll discuss next time. Okay, so request them to attend classes regularly now, because we have started the core of this uh, subject, that is CNN. Okay, and this is very interesting. You will like it, I'm sure. Okay, so request them to attend classes regularly now. And I will ask, okay, let me ask you only. Can we have one extra class tomorrow also? Because we have regular class on Thursday. So you can discuss with Wasim sir later, and you can inform me because we missed classes in last 2 weeks. So we need to compensate the syllabus. So if suitable to you, then tomorrow also during the same slot, 6 to 7, I would like to conduct the class. And Thursday again, we will have the regular class. So because we, last 2 weeks, we lost 4 classes, right? So we have to compensate it. Okay, so if you